Good evening to all. So thank you for joining. Today we are going to see UART protocol. So before going to see the on-chip protocol like APB, first we have to understand how off-chip protocol work. So how on asynchronous protocols are work. So today we will see the UART protocol. So and then day after tomorrow we will see the APB protocol, Verilog code. So today we will see the UART protocol and how to write the FSM and how to write the Verilog code for UART protocol. So yeah, you will get attendance link correctly today. So participation, but no invitation. So it is. I already scheduled the YouTube live so that the topic it didn't change. So basically, firstly, we have to know about off-chip protocols like a USB, like I2C, UART, and then SPI. So for that reason I changed the agenda. So tomorrow we'll see the ABB protocol. So is my voice is clear? Is my voice is clear now? I am audible to you. Is my voice is clear now? I am audible to you. So can anyone respond in chat box? Is my voice is clear now? So good evening to all. I hope my voice is clear now. Can anyone respond in chat box? So very good evening, Paratraj Singh. So Pradeep Kumar, good evening. Yeah, okay, fine. So let's see the UART protocol today. Yeah. Basically, UART protocol stands for Universal Asynchronous Receiver Transmitter. So it is off-chip protocol. So it is not based on clock. Why? Because of why we didn't use clock in UART protocol means. So if you take in two device like a on-chip device, if you are communicating within the chip, like if you, within the IC, there is a clock, so you can easily access the clock, so you can synchronize the communication between the two blocks or two devices inside the chip. But if you come to your off chip, like off chip means you are doing communication between the chip and peripheral devices like sensor, some peripheral devices like a sensor, keyboard, like kind of things. So if you are making communication between the chip and peripheral devices like mouse, sensors, and then some memory units, kind of things. So for that reason, we can't give the same clock to chip and peripheral device also. So for that reason, we are using the baud rate to make the communication synchronized in UART protocol, and also we are using some frame UART frame like a start bit and stop bit configuration. So if it is matching like a start bit and stop bit of your communication, if it is matches only, it will do correct communication. We can synchronize the communication between the transmitter and the receiver in UART. So and then this is the main thing why we didn't why clock is not important for UART. So that's why it's called asynchronous. So synchronous means it must be it must be based on the clock. So we are not using the clock in the UART, so that's why it's called asynchronous protocol. So it is a serial protocol. It will send data like a serially. It means bit by bit. So it having 8 bit of data. It will start from LSB. So it will start from LSB like a left hand side first bit. It will send the LSB bit one by one. So it's like a bit by, it will transmit by bit. So and then we'll move to the frame format of UART. So UART we already seen, like UART stands for Universal Asynchronous Receiver Transmitter. So why mainly UART having the frame work of like a data frame of like this only. So on start bit 8 data bit, and then on parity bit, and then on stop bit. So parity bit is optional. So let's see the how UART works. So UART works based on the baud rate. So why we need baud rate means to make the so, so you can find the yesterday attendance on chat box, and also you will get the today attendance on the chat box while in the session. So kindly register your attendance for yesterday and today. So you can find the link in chat box. So coming to the baud rate, so there are a lot of types of baud rate like in 9600, so 19200, so 115200. So these are the baud rates we are using. So baud rate is nothing but bits per second. So this is a baud rate. So you are based on the your communication, that the data transmission based on the baud rate only. If you are using the 9600, it is a lowest baud rate. So and then so it is highest baud rate ever, so in the UART, and then data bits up to 8 or 7. So and then parity bit is optional. So why, what is the purpose of parity bit means we can check the data is correct or not. To ensure the data, we can do the parity bit. So we can see, we can do the odd parity or even parity bit. So if it is odd number of ones or even number of ones, like kind of things. So for the security purpose, we are using the parity bit. And then stop bit, it is indicating the 1 byte of data as sent successfully. So it is like a indication. So it having the start and stop bit. So start bit, if you start bits like a low, so if you are giving low for so start bit means low, active low signal, it means 0. So every UART byte, like a 8 bit of data is called byte. So every transmission of 1 byte, it will start from 0, and then 8 bit of data, and then stop bit means high. So if it is start bit is 0, and then you can give the some 8 bit of data like binaries, and then stop bit is 1. So if it is a UART framework, so frame format, so it is the binaries of UART protocol, so it will follow that only. So you can see the what is bitrate means number of bits sent every second. So and then what is baud rate means number of symbols sent every second, where the every symbol can represent more than 1 bit. So and then let's see the frame format. So this is the frame format of UART protocol. It having one start bit and then stop bit. So you can see here start bit means, so how we can find the it is start bit. So if that particular bit having 0, so and then after that bit it will change to 0 or any data bit. So we can say that it is a stop bit, and then you can see the neckage. So data will be changing from high to low. So it will changing from high to low. We can say that it is a start bit. So and then we can, after that start bit, we can pass the 8 bit of data. So we can send the 8 bit of set data, and then it will change high. So it will change low to high. It's called stop bit. So this is the frame format of a like a UART protocol. So before going to that, I have one questions. If the both devices are like a transmitter, we having the transmitter and then receiver. So we having transmitter receiver devices. So transmitter device works based on the high frequency, like 115200 baud rate, high speed baud rate, and then receiver device will works based on some low baud rate like a 9600. So how will you make the communication between the high speed transmitter and the low speed transmitter UART device? So both are UART device only. One works based on the high baud rate, another device, another like a receiver works based on the lower baud rate. So how you can make communication? So normally if both devices are different means, like a transmitter and receiver are different baud rate means we can't make communication or synchronization between the transmitter and receiver, so we can't make communication. So there is a chance to we can data corruption. So the receiver and the transmitter will not communicate correctly, so there is a chance to data loss. So for that reason we have to use the like a buffer, like a FIFO memory. So I will show you in the whiteboard. So and then my question is it's like a device 1, baud rate is 9600. So it's a device 2, its baud rate is 115200. Its highest baud rate, it will receive data. It's like a receiver, it's like a transmitter. So it will transmit slowly, it will receive fastly compared to the device 1. So we can't make direct communication between them, so we can't assure that our binary data will go correctly. So the receiver will receive the correctly, so correctly cut it. It means we can't assure that we can't make the good communication between them. So that we are using the sorry so that we are using like a FIFO buffer. It is act as a buffer. It will store the data. So it is like a FIFO buffer. So the transmitter, low speed UART baud rate transmitter, will continuously writing into the FIFO. So and then here, so before writing it will act. So if it is before is empty means it having 0 value. So all the location it having 0 only. And then after writing, so transmitter, low speed transmitter, low baud rate transmitter will writing into memory continuously, like a firstly start bit. So and then start bit, and then start bit comes here, and then data bit is 1. So and then some 8 bit data bits. So it will continuously writing into FIFO buffer. And then this particular receiver, it will read from the FIFO buffer from the last location. So it will continuously reading from the FIFO buffer. So it is so we can make sure that my data will that there is no data loss. So why? Because of I'm storing into buffer, and then I'm reading from the buffer, so there is no chance to data loss. So there is no chance to data loss. So this is why we can make communication between we can make communication, and also we can safeguard the data from the two different baud rate transmitter and receiver in UART. So and then we'll move to the so this is the real frame format. So one start bit, 8 data bit, and then one parity bit. So we can use 2 stop bits. So why we are using 2 stop bit? 2 stop bit means, so if you are sending some like a if you are sending the continuous data bits, so you don't want to like that, so you want to send only 1 byte. So we can send like this way. 2 stop bit means it's like a double checking, like it is also security purpose. We send 1 byte of data correctly. So this is that. By using the 2 stop bit, we can make assure that we are sent correctly 1 byte of data. So this is the UART framework. So and then let's see the code. So before that, if you guys are really interested in this 21-day masterclass, you can convert into 1 month of internship on FPGA design. So these are the benefits you will get: all the details recording session, all the details presentation, exclusive project codes, and VIP community group for your doubt clearing. So and then you will get the internship confirmation letter from IETE. So and then you will get the 90 days course, LMS course access. So and then you will get also assignment and task, and then weekly live session, resume building ideas, mock test, and we are providing also internship certificate and also participation certificate for 1 month of internship. So this is the amount. So it's a discounted fee of just 999 will get. So our regular fee is 3999. So by using this link you can register for 1 month of internship. So it will close tomorrow. So let's see the coding part of UART. So I already written code, so it is very it having lot of logics, so that I just show you how to write that code. So before going to that, so while writing the code we can't give the baud rate, so we can't give the baud rate directly. For that we have to find the clocks per bit. It means uh, for to send the 1 bit, how many clocks is needed. So if you are, for example, your input, your FPGA having the 50 megahertz clock, so it will count up to 5 crore times for 1 second. So it means 5 crore clock cycles for 1 second. So based on your baud rate you have to find, so how many clocks needed to send the 1 bit of data. For that this is the formula for that. So for this is a formula for finding the clocks per bit. So clocks per bit is equal to frequency of input clock divided by frequency of UART. So UART, frequency of UART is your baud rate, it's 115200. So and then your input clock frequency, for example I'm taking 25 megahertz. So this is a 25 megahertz notation. So and then 25 megahertz by 115200 means you will get 217. So this is a 217 is the clocks per bit. So it means at every 217 clock cycle it will send one data. So it will send 1 bit of binary to transmitter or receiver to transmitter. So this is the main thing you have to find, you have to take into your mind. So this is a formula: clocks per bit equal to frequency of input by frequency of UART. So for every 217, so 217 clock cycle it will send one bit of data. So and then these are my input signals for receiver. So firstly I'm gonna show you the transmitter part. So this is UART transmitter. So for UART communication we have to write the two code, like a transmitter code and also receiver code. So we'll see tomorrow, we'll see today. So here this is the transmitter input and output signal port list. So I'm just using parameter like a clocks underscore per bit equal to 217. So it is a reset signal, active low reset, input clock, and then transmission data valid. So it's the transmitter data valid. DV means data valid, and then input byte. So this is the input transmission byte. Byte means this is our input data. We are gonna give the some binary, some inputs from this signal only. So this is the input signal for transmitter. This is the main input signal we are gonna use. We were gonna transmit and receive in the UART. So and then transmission active, and then output. See, these are the output signals are transmission done. So transmission serial. So why you can see here output rate serial, it means it will send bit by bit only. So that's why it didn't have any range, like a vector form. So you can see here my input is a 8 bit of data. So I'm going in the transmitter, it will perform like a converting the parallel data, like a parallel data into serial, like a, it will, so it will receive the parallel input and then it will give output as a serially. It will give by bit only, so that you can see the parallel output. So parallel input 8 bit of data, but you can see output. This is output serial. So this is my output signal for transmitter, it having the only one bit right, so we can send and we can give output as one bit only. So we can say that it is serial, so it will do serial transmitting like a bit by bit. So if the after the transmission done, so we have to notify that we have to give identify, so some for the knowledge purpose we can use done. So it means I send one byte of data to receiver. So for that reason, if it is high means, if done signal is high means I sent one byte of data to receiver. So for that indication we are using this signal, particular signal transmission done. So and then so in FIFO, so sorry, in UART we having the three stages like a start stage, data bit stage, and then stop. So we are having three main stages. So three main bits like a start bit, data bit, and then stop bit. So we have to write the FSM for that. So you can see here, so this is the FSM. So ideal is my first state, and then start bit is my second state, and then data bit is my third state, and then stop bit is my, so where is the DV? So DV, so it is a data valid. So it means if I'm given some if it is high only, it will move to the next state. So you can see in the ideal condition, so if it is high only, it will move to the next state. So this is some internal signal for the internal state machine changing. I'm using this. So for to make the logic correctly, I'm using this data valid signal. So data valid is nothing but your input signal ready. So I can given to transmitter like a kind of thing. So and then data bits, and then stop bit. So these are my states like four state: ideal state, start bit, data bit, start bit, data bit, and stop bit. So these are my internal signals like R underscore SM underscore main. So it is a state machine. So FSM state machine. It will base on these states. So and then I'm using the clock underscore counter to count my clocks per bit, and then R underscore bit index. So bit index means so I want to transmit these 8 bit of inputs at the serial output. So I can send only one bit at a time. So for that I want to change the index. So firstly I want to first LSB, and then second LSB, and then third LSB. So I want to change the LSB bit. For that I am using these variables, that particular internal signal bit index, to choose my index. So based on the index value it will send the value, it will send to receiver. So and then you can see here I am using some temporary memory r underscore tx data. So it is I'm storing here output. I'm just storing the output, and then I'm assigned to this variable. So I just show you where I'm using. So firstly you will see the reset condition. If it is in the reset condition, my state machine will stay in the 0, and then if it is not in reset condition, it's active low. Active low means, so if it's even the clock, it will 0 means it's a reset, not in high. So and then it will move to this condition. You can see here output transmission underscore down. It means at this stage itself we didn't done any transmission, that's why I'm assuming 0. So and then it will move to case. So based on the case statement, first state is ideal state. In the ideal state my clock counter and bit index are 0, and then my serial output serial like a transmission serial I'm given like a 1. Why I'm giving means, so it is if I give a 0 means it is a start condition. So I don't want to make the start condition in the ideal state. I want to make a start condition in my start bit, so that I'm giving 0. If I give the 0 1 0 here means it's act like a start condition. So for that reason I'm just give 1. So if if my data valid is 1 high means I will move to my next state. So if my data valid is high means I will move to my next state is a start bit state. So and then output, and then so output tx active 1, and then data. You can see here I am just storing input data. So I underscore input byte, so it is my I underscore tx underscore byte, so it is my input data. I'm just assigning to my temporary variable or like a receiver transmission data. So I'm just assigning to that particular temporary variable. So and then I will move to my start bit. So in the you can see here in the start bit I'm just giving 0. So I'm just giving for 0 for output transmission of serial. It means I'm making my start condition. So my start condition is firstly it having 0. My start bit must have is 0, so that it will start the UART communication. So I'm just giving 0 for that. So and then here you can see I just increasing my counter to. So why I am using this counter means you can see r underscore clock underscore count. If less than like this, if it is true means it will execute this. So why I am using counter means I want to count 270, so then only I can send the another bit. So for that counting, for that reason I am using the counter. So you can see here counter. So so you can see here, if it is true means it will stay in this same state. So you can see if it is true means it will stay in the same state. Why? Because of I'm just assigning r underscore sm underscore main means, so main, it's my state machine. I'm staying, you have to stay in the same start bit state. So and then if it is fail means it will move to the next it will move to the data state, so data bit state. So if it is fail means I'm just resetting my count 0, and then I will move to my data bit state. So it's like a just a FSM only, it is easy. So and then in the start bit state, so in the start bit state, this is the main thing. So I'm just giving some my parallel input to my serial output. So this is my parallel input r underscore tx data. So I just stored here, you can see here my input data are stored in the temporary memory. So this is the temporary memory. So under r underscore bit underscore r underscore bit underscore index, it means it will increase. So you can see here I'm increasing here I'm increasing my bit index. So at the this it stores some 8 bit of values. Based on the index value it will assign to the output serial. So it is my transmitter output underscore o underscore transmission serial. It means my transmission output. So if and it is just assigning, so I'm just counting for the clock, I'm just counting the counter to send the to assign the bit by bit. So and then you can see here if r underscore bit underscore index less than 7, it means it will up to, if it is less than 7 means I'm just increasing my index. So every time index changing, so it will I can see changes here. Firstly it having 0, and then 1 2 3 4, it will go up to 6. So 0 to 6. So and then 0 to, so at the every memory location it will send. So if it is having means r underscore tx underscore data of 0, it means this particular variable 0th memory location whatever it having, I'm assigning to this variable, this signal. So it's like a parallel to serial. So say parallel to serial converting. So and then if it is fails means it will, so if the bit index more than 7 means it will fails. So if it is fails means it will come here, so it will move to the stop bit. So it means I'm just changing my index all 7 bits. So it's like I'm sent like a 8 bit of data. So it is now time for the stop bit. So that I'm saying you have to move for stop bit, so it will come here. So and then you can see here output serial, so output transmission serial equal to 1, it means I'm saying it is a stop bit. So stop bit is 1. So So we can see here stop bit is 1, I means 1. So if it is 1 means after the 8 bit, if we, but the receiver UART sees like a after the 8 bit, if it is see the high means it will take at say it is a stop bit, so it will store some 8 bit of values, 8 bit of values. So this is a stop bit, and then if r underscore clock count is, I'm just counting to stay in the stop bit, and then after that I can after that you can see the output transmission done equal to high. It means I'm saying I sent 1 byte of data to receiver successfully, so I can say that 1 byte of data as sent successfully. So again I'm going to my ideal state to send the again to send the next byte. So for that it will move to the ideal state. So this is a UART transmitter. It's simple only. So in start bit I'm giving 0 for output, and then in the data bit I'm just converting the parallel input to my serial output like bit by bit. In the stop bit I'm just giving for 1 for my serial output. So and then I'm going to next state is ideal in the stop bit to make the next byte transmission. So this is the UART transmitter. So let's see the UART receiver. It's the same only, same signal. So but here we can see the differences. RX TX means transmitter, RX is a receiver. So same thing, but you can see here my output is 8 bit of data. So it will receive, the receiver will receive the data serially, and then it will store in one temporary memory. So it will like a parallel, so it will convert the serial to parallel transitions. So it will receive serially and then stores in parallel, like a memory. So we can see the output parallelly in the receiver. So my receiver, so transmitter output is serial, but receiver output is like a parallel. So we can get the 8 bit of data at a time. So at same bit, same stage, like a RX start bit, data bit, ideal, and then these are the same states, and then I'm adding another bit is a cleanup bit. So state is a cleanup state. So basically same signal as like a counter in between tags, byte, data valid, then state machine. So same only. So here I'm using the passage of clock. So you can see at the time, at the ideal state, my data valid is low. So and then if I received, you can see this is my input signal, serial input was it will receive only 1 bit. If it is received 0, it means I detected the start bit, like a 0 is a start bit, no. So it will assume like this is a start bit, so I have to move for my start bit, or else it will stay in the same state. So in the start bit, it will check half of the count. So you can see here it will check the half of the count only from 2172. It will check half of the 217. Why? Because of in the half of the clock pulses, if any changes happen in values like this particular signal. So if it is changes means it will stay in the it will move to the data bit, or else it will move to the ideal state. So and then I'm just increasing my counter. I'm staying in my like start bit condition here. So and then in the data bit, so I'm just using my counter to receive the 1 by 1 bit by using the counter. So r underscore clock underscore count. So and then here you can see here is a main point, so my main logic. So I underscore RX underscore serial is my input signal for receiver. It will receive from transmitter bit by bit. So every bit I am just storing into my R underscore RX underscore byte. So it is my temporary variable. So it is that. So it having 8 bit of vector, so you can store 8 bit of data. So I'm storing into, I'm receiving bit by bit. So you can see this it having only 1 bit, it can receive. So I'm receiving bit by bit, I'm storing into this memory. So it can store 8 bit of data. So and then where it can store means based on the bit index only it can store. So I'm just increasing my bit index here from 0 to 7. So at the 0th location it will store the first received bit, and then so it will store up to 7 bits. After that it will move to the stop bit. So this is the logic. So here this is like I'm storing into some temporary variable in my data bit. So and then in the stop bit condition, so after that it will move to, if it is syntax which is base like a bit underscores in index, if it is fails means it will comes here, it will move to the stop condition. So you can see I'm r underscore sm underscore main means I'm changing my state to my stop bit. So in the stop bit it will continuously increment clock and then data valid. So I'm in the stop bit it will detect 1, and then I'm saying data validity is high. So it means I just received 1 bit of data. So for that reason I'm just saying my receiver data valid. So receiver, it's like received 1 bit of data, so that data is valid. So I can say it's I'm saying like a 1. So I'm saying 1 means data is valid. So and then counter equals 0, and then it will move to the cleanup state. So cleanup state is my last state in my receiver. So in this cleanup state you can see here I am moving to my ideal state. So my next state machine is ideal state. I'm after the cleanup state, and then by data valid is 0. So if I data valid is 1 means it is refers to just received 1 byte of data. For that purpose I'm just giving 1 for data valid. And then in cleanup state I'm just assuming 0. Why? Because of I already received 1 byte of data, and then I want to receive other bytes. For that I'm just changing to 0 data valid. If the data valid 0 only, if it is 0 is means it will receive the next it will start the next byte. If it is high means if it is stay in the high. So my data valid is high only at the all time means it won't start the next byte. So this is the logic why we are using data byte. So data valid, if data valid is high means I just received 1 byte, and then I must change to data valid equal to 0. So then only it will move to the next byte. So this is the logic I'm using here. So my first logic is that only data valid is 0. So and then I'm just assigning some continuous assignment. So this is my temporary stored value. So data temporary stored this is temporary stored memory. I'm just assuming to my output, and then this is my data valid for temporary. So temporary, and then this is my output data valid signal. So this is a receiver transmitter. So sorry, this is a UART receiver, and let's see the test bench for that. So these are the bit. We have to find the clock bit period. So clock bit period is this is that 8600. How we can find means, so I'm using the 25 megahertz. For 25 megahertz it will take from 25 megahertz you want to make one clock cycle means it will take 40 seconds, 40 nanoseconds. Yesterday also we seen that for 50 megahertz it will take up to 20 or 20 nanoseconds for 50 megahertz. For 25 megahertz it will take 40 nanoseconds to make the one clock cycle, like a one duty cycle. So and then this is my clock per bit, we know that. And then if you multiply both clock period nanosecond and then clock per bit, you will get the 8600 something value. It's like a time period of the clock, so time period of the bit. So for it, why I'm using this means to give the delay. So I'm just instantiating both modules, like a transmitter module and then receiver module, in my test bench. Then only I can access the both signals. So then I'm just using some wire to connect the transmitter and receiver in the module. So you can see here, this is the your transmitter output serial. This is my output. So this is output my this is my output for your transmitter module. So I'm using one here wire here, w underscore tx underscore serial, and then you can see here output byte. So and it will connected by the output y w underscore rx byte. Why? Because of I'm just assuming, I'm just giving this signal to this signal value, and then it will connected by this signal, so I can get the output at the receiver. So this is like a connecting the both modules by using the wire. So if the right like a transmission active means it will choose serially, or else it will choose one. So and then it is a creating of clock at the at every. So you can see here clock c underscore clock period at nanoseconds. So it's like a 20 nanoseconds. At every 20 nanoseconds it will toggle the clock. So r underscore clock is my test bench clock. So at every 20 nanosecond, you can see here this 40 divided by 2 means 20. So at every 20 nanosecond it will toggle the clock. So and then this is the passage, and at every passage I'm just writing. So I'm just, you can see here r underscore tx byte equal to 3f. This is my first 8 bit of data. I'm just transmitting to receiver. So then here I'm checking if my receiver receiver byte, if it is equal to 33f, like I'm just written 3f and I have to receive 3f. If it is receives 3f means my test is passed, or else my test is failed. So this is a test bench I did here to check only one value 3f I transmitted, and then I have to check in my receiver. So it is only for checking that rx part. So I'm just transmitting some value from transmitter to receiver. I'm checking the receiver, so it will check, it will receive the particular value or not. If it is not receiving means there is error in my logic, or there is the error in my code, or else my test case is fast, or else my test case is passed. So let's run this code. For that I am going to use Gusta sim. So it is like a simulator, so you can easily access. It is open, it is not open source. There is a cracked version for Gusta sim simulator, so you can access that easily. So this is the run.2 file for that. So I just open Gusta sim. Yeah, you can see here my test is passed, correct byte received. So this is received correctly. So you can see in the waveform also. So you can see here 3f I received. Where I am receiving means UART, or so you can see the signal name here, r underscore rx byte. So this is my received byte. It is having 3f. So and then you can see here it will changing. So you can see here firstly. So I said no, already it is sent bit by bit. So how it is means, so this is my output signal from the receiver. For receiver, this is output signal. So this you can see here r underscore rx underscore byte. This is my output signal. For firstly it having 0 and then 1. 1 is my 0 1. So 0 1 is my start and data bits, and then 3 and then 7. These are my data bits based on my binary inputs. So I am giving bit by bit only. So that's why it will show these kind of things like 1 3 7 0f 1f. So it will showing some binaries, so binary values in the decimal form, in the hexadecimal form. So why because of it will send bit by bit. So it can firstly if I send 1 means it will I can see in my receiver 1. My next bit is 1 1, so I can see the 3, and then my next bit is 1 1 1, so I can see the 7. If my next bit is 0, it means 0 1 1 1, so I can see the 7 in my output in the rx byte. So this is the reason why I am getting the 3f at the last of the so you can see here I will receive the 3f at the last. And also you can also see that done rx tx will be done like a data valid signal. So by using these signals we can easily find the where I am getting. So you can see here my received a 3f in my r underscore rx underscore byte. So this is a way of writing RTL code for UART. Yeah, you can use also EDA playground for this. You can also use this code to check yourself in EDA playground. So for that, if you want to see waveform means, you just need to add this like in the test bench. You just need to add these two lines like a dump variables for EB to see the waveform in your EDA playground. So you can use this code to check the what in EDA playground you can access. So you can use it. So it is both the same only. EDA playground and simulators question sims are same only. So it's like I'm having that, so I can do n number of times. If I need to EDA playground means I need to have access for that. So there's maybe there is you will receive some issue in EDA playground. For that reason I'm just using question sim. So this way of writing RTL code in code for Verilog, code for UART in Verilog. So let's see the ABB. The ABB is a protocol, on-chip protocol. So we seen like a off-chip protocol from chip to peripheral device. Tomorrow we'll see the on-chip protocol inside the chip, how it is communication between one block to another block by using the APB protocol. So APB is a low performance, low speed, low bandwidth, low frequency protocol. So it will used for peripherals only. So let's see what are the protocols is they having. So we know that already we seen like AXI, AHP, APP. So we'll see tomorrow with the APP protocol. So what are the signals? So how the signal is differentiating between AX and APP. So both are AXI, APP. So coming to the AMBA protocol, it having APP, AHP, AXI. So each and every protocol it having some signal specification. So P means APP protocol signals, and then some it having some A means AXI protocol signals. So this is kind of own specification for signals. So it will take some time. So we will see tomorrow with the APP protocol. So thank you guys. Thank you for listening. We'll see tomorrow.